Panetta. I'm the Vice President of Engineering at I-Gard. And it's my fault when something doesn't go right. My boss tells me anyways. And my wife, unfortunately. So I'm still late. She's not here. All right, so we're going to discuss the practicality of high resistance grounding. There are some things a lot of people still don't understand. I'm sure you guys all understand high resistance. Who uses high resistance grounding? Who uses it? Sometimes. You're not winning. No. Huh? No, that's a different resistance. You can have resistance to antibiotics, yes, but resistance in electrical systems is a little bit different. So please let me know if you guys have heard these ones before. So we have two types of systems out there, delta and Y. And we can ground each one of these things. Corner grounded Y, delta. Has anybody seen these? And I've got an hour, so I can go as fast or as slow as you want to go. So if you know the answers, shout them out. If you don't know the answers, I'll tell you what they are. But you've seen these ones, right? Are they useful?
Yeah, I can really at the midpoint, right? Midpoint grounding on delta.
Yeah, that's the next one.
Okay.
So you haven't seen the corner grounded delta system. You have to understand your electrical system. So who's read the Canadian Electrical Code where it says qualified people need to work on resistance grounded systems? Why do qualified people only need to work on resistance grounded systems? I think qualified people need to work everywhere. Right? So if you have a corner grounded delta system and you're an electrician, who are electricians and who are engineers in here? Any engineers, put up your hand. All engineers. Electricians, people who do work other than in their homes. Nobody. All right, so if you're in the electrical field and you see a delta system and you're measuring phase to phase and phase to ground, and you measure 600 volts phase to phase, 600 volt phase to ground on two phases, and 0 volts to ground on the third phase. What do you think you have? You have a corner grounded delta system, right? According to this scheme, right? You could have a ground fault if there was no ground in the system. So that's why I'm saying qualified people need to understand what's going on. So this is the one that you're used to. So you measure on a, let's say example, you have a 240 volt system. 240 volt phase to phase, that's what we're going to measure here. 120 volts from here to ground, and from here to ground. For sake of argument, let's call this the neutral. Okay, because you can make the neutral anywhere you want. How many different voltages can you get out of this system?
It depends where you tap it along the...
Well, there's the ground right there. Come on, I'm not trying to hide anything.
300.
3 voltages, what are they? 208. Exactly. So you're measuring, you're an electrician, you're measuring 120 volts to ground on 2 phases, 208 to ground on the third phase, and 240 volt phase to phase. What do you think you have? You have this. But you have to recognize that you have this. So when you go into a facility and you're measuring voltages, you have to understand what the grounding system is of that before you start making your measurements, so you understand what you have. This slide, this is going to be available to everybody if you want, so you don't have to take pictures. If you're going to take a picture, let me know and I'll show you my good side.
You don't have one.
Only my friends. So, in a Y system, we have the same thing. Take the neutral point and you connect it to ground. So let's go back. Ungrounded systems. The Canadian Electrical Code says for ungrounded systems, you must have ground fault detection. There is no ground fault protection, only detection. Solidly grounded system, The code says if you have a system that's greater than 150 volts to ground and greater than 1,000 amps, you must have ground fault protection. Must. And you have to trip in less than 1 second for over 150 volts to ground or 2,000 amps at 208. This is a solid grounded system. This is another solid grounded system. This is the one where everyone's used to this one, right? 120, 208, it's a classic. 600, 347, 480, 277, this is what they use. Resistance grounding. Resistance grounding is a little bit different. There's two types of resistors that we can use in resistance grounded systems. There's low resistance grounded systems, and there's high resistance grounded systems. The difference between a low and a high resistance grounded system is the amount of current that we have flow through the system. If you limit your fault current at, on a system that's less than 5 kV to 10 amps or less, it's a high resistance grounded system. The benefits of a high resistance grounded system, so for example, you have a 600 volt, you put a 69 ohm resistor there. You limit your fault current to 5 amps. You don't have to trip. Canadian Electrical Code, the National Electrical, who does work in the States? You do it. You don't have to trip. Right? So you have increased productivity because the most typical fault that you're going to have in an electrical facility is a single phase to ground fault. Who has ever seen a 3-phase fault occur all by itself in the one? Nobody. It's rare that you have a 3-phase bolted fault. Although we have to measure all of our equipment to 3-phase bolted faults, they're very rare in occurrence. Most faults begin as single phase to ground faults, and they propagate to a phase-to-phase or a 3-phase fault. Because when you have, for example, a 2,000 kVA transformer, you have a single phase to ground fault on a solid grounded system, you can get as high as 30, 40,000 amps flowing through that point of fault. You damage the equipment. You deteriorate the insulation. You have molten copper, molten steel around the insulation. The insulation at that point is air. So you contaminate the air, and we create a phase-to-phase or 3-phase fault. That's why Z462 and NFPA 70E state that if you use a resistance grounded system, you have an arc flash mitigation technique. Why? Does the resistor change the incident energy? No. Who does incident energy studies? Who does arc flash studies? Nobody. Good. You contract that. You sit next to somebody who's contract. All right. So when we calculate incident energy, it's based on the 3-phase bolted fault current and time. How long is a fault on the system for? Ajay was talking about kilowatt cycles. They use kilowatt cycles before incident energy. Now it's calories per centimeter squared. And we have to measure that. Time is directly proportional to incident energy, or incident energy is directly proportional to time. The faster you trip, the lower your incident energy. We don't change the current. The resistor here does nothing for a 3-phase bolted fault, but all of our calculations, where's Randy? Randy, you do it. How come you didn't say anything? Anyways, incident energy is directly proportional to time. A resistor is not going to lower incident energy. What it does do is it decreases the probability of having a single phase to ground fault, which is the most typical fault that you can have in the industry, from propagating to a 3-phase fault, and hence lowering the probability of having an arc flash event. So that's why resistance grounded systems are arc flash mitigation techniques, because they lower the energy at the point of the fault such that you have no damage, very little damage, and you have an arc flash mitigation technique. Now a resistor, a 69 ohm resistor, will be very, very, very small, and it protects the entire secondary of the transformer. Whether it's a 500 kVA transformer or generator, or 5 MVA transformer or generator. One resistor this size, or half this size really, will protect the entire secondary, so the entire secondary or the distribution system is fully protected as an arc flash mitigation technique. Unlike, who uses arc flash relays? We produce arc flash relays. The problem with arc flash relays is that they only protect a section of gear where you have the arc flash mitigation. Differential protection only protects a certain portion of your gear. The resistor protects the entire secondary. So when the neutral is available, we can just put a resistor on it. It's easy to calculate the size of the resistor. What you want to limit the fault current to, and the line to neutral voltage. So if you had a 4160 volt generator, you want to limit the fault current to 400 amps. 4160 divided by root 3 gives you the neutral voltage, 2400 volts, 400 amps, 6 ohms. Yes?
But if you leave it long enough, right? A ground
Sorry?
fault. If you leave a ground fault long enough.
Is the ground fault long enough?
Yeah.
What
You
do you
can
mean?
leave it for 2 days, for a week, or whatever you want, right?
On a low resistance grounded system, no. On a low resistance grounded system, you have to limit the fault current to a certain value.
On a higher
That-
resistance. on a
That
higher
value is typically 10 seconds or 60 seconds. On a high resistance grounded system, they say that you have to have qualified people to determine how long the fault is on the system for. So now you have to think, okay, I know I have a fault. I have a fault in that motor. How long can you leave the fault on the system for?
What I'm getting to is that the probability of arc flash increases because if you leave it long enough,
Okay,
you have a face-to-face short circuit
Sure.
sometime.
I agree with you. What have you done? When you have a fault on your system, haven't you just converted your system to this? So now you have a solidly grounded system.
Functioning.
It's functioning as a solidly grounded system. So we went from a resistance grounded system, you went to a solidly grounded system, now different rules apply. So yes, you have to do something before something else happens. And this is where I think the qualified person is meant. The qualified person needs to look at this and say, okay, now my system has changed. What do I need to look at now? Not necessarily to work on the equipment, but to understand the implications of what's happening. They can either clear the fault as quickly as possible, or if they understand where the fault is, order the piece of equipment that needs to be faulted, have it come in, replace it right away, and the fault is cleared. So yes, when you have a resistance grounded system is an arc flash mitigation technique. Once you have a ground fault, you no longer have a resistance grounded system in that sense of the terminology. You have basically a solidly grounded system. But the next fault will be a doozy. But we have equipment that will detect that second fault and isolate one of the feeders that you deem to be of lower priority. So we can go that extra step and give you that protection if you want. So when you get a ground fault current has to return back to the source. Ground fault current doesn't go to ground and just stay there. It has to return back to the source, and it uses the bonding network of your system to return back to the source. I didn't spend a lot of time on the bonding network because regardless of whether you have an ungrounded system, a solidly grounded system, a resistance grounded system, either low or high resistance, the bonding network is exactly the same. Sometimes if you have a generator, they use a step-down transformer and a resistor. Same thing happens. You got a ground fault, current is limited by the resistance on the secondary of the transformer, and this provides a path. If you talk to Edmundo after this, he'll be happy to give you a copy of the slides. If you have a delta system, and you want to convert it to a resistance grounded system. Does anybody have delta systems? You have a delta system. You have a delta. Why? Why do you have a delta system? Why?
It's just it's when the generators are disconnected, that's when it's still not grounded. But otherwise, when the breakers are closed, it's all grounded.
Okay. And you, why do you have a delta system? Same system? You inherited it. You inherited the delta system. If you want to convert your ungrounded system to a resistance grounded system, you can do it very easily by using a zigzag transformer. A zigzag transformer is designed in such a way that under normal system conditions, you have a high impedance device. Very, very low current flows through the delta system, or the zigzag. But when you have a ground fault, this is the mechanical and this is the electrical. So when you have a ground fault, the current goes through the zigzag back to the phases. So it's returning back to the source. You can also use a Y-grounded delta. Y-grounded delta, you have single-phase transformers. They could be 4160 to 120. You have a ground fault, and the current returns back this way. Or you can have a Y-grounded open corner delta. What we've done here is opened up one of the corners, put a resistor in there, and that resistor impedes the fault current. And all the values here are you can use. And they're on our application guides as well. So Sergio was talking about the capacitive curve. When you have a normal system, you have capacitance. Think of your cables as capacitors. Because what happens is you have two potentials isolated by isolated from each other by an insulated medium, and an insulated medium is the insulation on your cable, or air. If you have a bus duct, air is an insulated medium. That's a capacitor, but that capacitor is distributed throughout your entire length of your cables, your busways, and everything. So what I've done here is I've drawn the capacitors not as a distributed capacitance, but as a lumped capacitor. So this is what happens, your voltages. 347 volts phase to ground. And there's your capacitance, and they sum up to 0. Because the capacitance going there, there, and there, add up to 0. That means if you put a 0 sequence CT right here, even if you have a fault, you're going to measure 0. Now we have a fault. So we're going to have a fault on C phase. The fault current returns back to the source. You have very, very low current flowing in an ungrounded system. The amount of current flowing in the ungrounded system is proportional to the capacitance and the distribution of your system. So it looks like this. So the fault current is equal to the resistive current plus the capacitive current. The current's going through here plus the current going through the capacitance. This is why Ajit said that the resistive current must be equal to or greater than the capacitive current. And the fault current is, I haven't drawn it properly, but my resistance current is smaller, but I did this for a different reason other than showing you which current is larger. The other school of thought is, remember, the line to ground potential shifts when you have a single phase to ground fault. The faulted phase and ground is 0 volts. The unfaulted phase is to ground's full line-to-line potential. When you have line-to-line potential on 2 of the phases, you're measuring 600 volts, and 0 volts on the third phase, which is faulted, you have a ground fault. That neutral shifts. So part of the problem we have when you do that, when you have that neutral shift and the unfaulted phases elevates the full line-to-line potential with respect to ground, you have to watch out for SPDs, surge protective devices. And we've had a facility in Toronto that a data center changed their entire system from solidly grounded to resistance grounded. And they hired an electrical contractor or an engineering firm to go in there and do all this. And engineers are great because they think that if one surge protective device is as good, 100 must be better. So what happens when you get a ground fault and you have a surge protective device? Surge protective device is an MOV, and this is the curve, voltage to current indication of the current going through the MOV. So when voltage to ground is normal, you measure 347 volts to ground is normal, everything's okay. When you get a ground fault, we now shift the two unfaulted phases to full line-to-line potential. Now we're not inside that operating range of the MOV anymore, and what happens? You get a three-phase short. One phase is already faulted, the other two are 600 volts to ground, you get a three-phase short. And if that happens to several VFDs or several SPDs, you have a big problem. You remember when Canada Day first started in Canada or in Ontario? This is what happened. The first Canada Day, I was called out to this facility to find out what was going on. And it was specifically because of the SPDs. So, but they say you can use a surge protective device on a resistance grounded system, but that surge protective device has to be properly rated for use with the resistance grounded systems. That means the line to line potential and the line to ground potential are equal. So, but the best part of having a resistance grounded system is now you're able to locate where the fault is. And we do that by changing the value of the resistor here. We change the value of the resistor with this contactor. So 1 second it's open, 1 second it's closed, second it's open, second it's closed. We can actually go around, and when you have a fault on the system, you can see that this, if you had a zero sequence CT over here, you're seeing indication, you're seeing a change. This was Agile was talking about. You see a change in current. Over here you see the change in current. Over here you see the change in current. You don't see it here because there's no fault down here. You don't see it here because there's no fault down here. And once you pass the point of the fault, you don't see that change in current anymore. So you can find the fault very easily, less than 1 hour in any size facility. So the capability is there to locate where the fault is. The willingness may not be there.
And what's the cost?
The cost,
You remove the G element on the breaker with this
okay,
sensor.
you want to look at cost now. So let's look at this. You don't have a neutral. So you don't have the distributed neutral. You don't have 3-phase 4-wire switchgear. You have 3-wire distribution. You can actually take out the G function of all your breakers, and you can probably save a lot of money by just using a resistance grounded system.
So that G function would be kind of equivalent to the cost of the sensor?
The G function is useless because we're limiting the fault current to 5 amps.
Cost-wise, would it be comparable to a sensor that you install on one of these sensors?
Oh, more than comparable. How many feeders are you looking at?
Depends.
Even 2 feeders. It's very comparable. And let's assume you don't have a distributed neutral, but you have 347 volt lighting. So now you put in a step-down transformer from 600 to 600 347. Now your electricians are changing ballast with a 100 kVA transformer instead of your 2 MVA transformer out front. Much less incident energy, it's safer for them.
So if you did want to convert over to an ungrounded system.
To an ungrounded? What? No, not ungrounded.
Sorry, a
Resistance
grounded system.
Yeah.
There's already a wide systems in place. They're already using the 347 for
Right.
the lighting there. You want to then have it as a resistance grounded system. You've got to put in place a whole bunch of 600 to 600 347 transformers in order to continue providing that 347 where you need it.
Right.
Right? Is that what?
Yeah, that's what you would have to do, because you, well, oddly enough, and I wasn't going to mention this, in Canada, you are allowed to have a resistance grounded system with a distributed neutral. I don't agree with it, but you're allowed to have it. The rules are different. You have to trip instantaneously if you have a ground fault. So you don't get the benefits of having a resistance ground assist because you have to trip immediately if you have a ground fault. But I don't like it specifically because I think it's dangerous. Let's say, for example, say these lights are 347 volts, and I'm connected to a 2 MVA transformer. And I'm going to change the ballast on these lights. So I'm going to get my electrician to do it because as an engineer, I don't do work. I only instruct people to do work. I can design many systems, but I'm not really qualified to work on any of them, right? So I get an electrician to do the work. And what's the first thing the electrician is going to do if he's going to change the ballast? Let's assume the ballast is 20 feet in the air. So he gets a ladder, scissor lift. He's going, oh well, first thing he's going to do is going to hopefully shut off the lights, right? Let's assume he does that first. So he shuts off the light. When we switch the power off, it's a single phase switch, right?
Yep.
All right? Now let's say he does everything properly. He locks it out, tags it out, measures the voltage phase to phase and phase to ground. There's no phase to phase because it's a single pole switch. So he's measuring phase to ground and he gets 0 volts. And it's connected to A phase, right? He locks it out, tags it out. It's confirmed de-energized, right? So now he's going up to change the ballast. Does he take his gloves off? He could take his gloves off. It's allowed, right? He may want to use his gloves on because he doesn't want to get them dirty or get his hands dirty, but he can take his gloves off. Now let's say, for example, you have another motor in the facility that has a ground fault. Totally aside from where he is, in a different part of the plant, same transformer. We've elevated that neutral to 347 volts, right? What happens? What happens to your electrician?
He's toast.
And all you can do is apologize. Right? So, have we done him any favors? He's done everything properly. He's done everything he's been trained to do from the day he became an electrician and he got electrocuted. Why? Because the Canadian Electrical Code allowed a distributed neutral on a resistance grounded system. Now, I don't think any have been used, but there's a danger in that being done. This is why you disconnect the neutral and you get the full benefits of having a resistance grounded system because you don't have to trip. Your neutral is never going to become energized because you don't use a neutral.
You still got to put in those transformers with that.
Yes, you are. And now when you calculate incident energy, you have much less incident energy because you have a 112 kVA transformer as opposed to a 2 MVA transformer feeding those ballasts. So the incident.
Right. So in your cost benefit though, you still going to save on the whole wire part of it.
That's right.
You've got to create these other.
Right. And we had one facility in the United States who's converted over 100 substations from solidly grounded to resistance grounded solely as an arc flash mitigation technique. And what they found is they saved more money in 3 years on motor repair costs than more than paid for the capital investment of all those resistance grounded systems. So you have much less damage at the point of the fault. So it is worth it, but you have to look at your facility.
Yeah.
So we're still pulsing. We found where the fault is. We can clear the fault if we want to and switch back to a resistance grounded system. We can repair that fault because typically, if you have a fault, it's going to be in a motor. It's going to be in the terminal box. You can open it up, tape it up, put it back into service. No damage at the point of the fault. Had this been a solidly grounded system, there'd be smoke coming out of here. You would be able to find the fault, but that motor's gone. So you were asking earlier about finding the fault through conduit. Bear with me a second. So this is our DSP system. I'm going to turn on the pulsing. I don't know if you guys can recognize my thumb. So it's hard to tell, but concentrate on that bar graph at the bottom. If you try to look at the numbers themselves, you're going to go nuts, because digital numbers change so fast. So right around Conduit. Zero sequence CT, right around Conduit. So now you can find the fault without opening up any doors. Because what you're looking for is the pulsing. Because you've heard the expression, current takes the path of least resistance, right? It's not true. Current takes every single path available. So you can see the pulsing. And one day I promised myself I will get a better video of this. So right around the elbow. So now I can find the fault without opening up any doors. And I've been to some facilities where they actually label the conduit. Say for example, you're at an MCC. They label the conduit exiting the MCC, which bucket it's coming from, and what motor it's going to. So I don't have to look at it and say, okay, let's open the bucket, look at the cable tray. It's this one, it's this motor right here. Right? Because what you want to do is create a safer environment. So your conduit is labeled. It takes a lot of effort to do that. Right? So here we have a resistance grounded and solidly grounded system during arc flash studies. There's much less damage in the resistance grounded system than the solidly grounded system. Now we're going to get into our sigma. Our sigma relay is basically monitoring the resistance of the resistor. What happens is, when you have a resistor, we have to monitor the integrity. According to the Canadian Electrical Code, you have to monitor the integrity of the resistor on any resistance grounded system. So what we do is we measure the voltage going across the resistor through this NGR-SX, and we measure the current through the zero sequence CT. And we compare them to each other. We get this value for voltage, we get this value for current. This green line is the line that it should follow if your resistor is okay. You get a fault, current goes up, resistance goes up, voltage goes up, resistance stays the same. You don't get, say for example, there's something wrong with your resistor, voltage goes up, current doesn't increase. You have an open circuit. There's a problem with the resistor. And this is only when you have the capability of measuring voltage and measuring current. If we don't have that capability, say for example, in the mining industry, we have to do this even when the voltage is off. We have to monitor the integrity of the resistor when the voltage is de-energized. We do that through injection, and we can actually tell if the motor, or if the resistor is open or short-circuited, even with YY connected PTs, and soon, even if there's a transformer coupled to a resistor on it.
So this monitoring just when the resistor is actually on, and changing the resistance?
Always. It's always on. What do you mean when you're changing the resistance? I mean when you're pulsing?
Yeah.
When you're pulsing, it is possible to fool this relay to think that there's something wrong, but when you're pulsing, it doesn't really stay at an elevated resistance long enough for you to detect it, because it always returns back to normal. When you're pulsing though, it's thinking, okay, are you sure the resistor is okay? Because we're doubling the resistance in most cases.
But it depends on the manufacturing of this and the quality of it, or no, just the general, you have to just look at this.
In my resistors, we rarely have a problem that we manufacture here. typically what happens is if you're in an area where you have a high corrosive environment, if you're near the ocean, it's possible to get deterioration of the connections, of the cable, of the wire. I'll give you an example. See this point right here?
Right.
This point right here monitors the integrity of the connection from here, and you can move that point right to the transformer neutral. So you're going to monitor the entire length of that neutral cable as well.
Yeah, no, because it said in Canada doesn't have any corrosion, so
Canada does not have it.
yeah, that's why you look.
Well, it depends where you are.
It usually doesn't have that salty place.
Atlantic Ocean, Pacific Ocean, we do work all over the place, so. Potash mines. So then we also have an absence of voltage detector that we've developed, and you're going to see this later. What the absence of voltage detector does is it monitors to see if the voltage is truly de-energized. Now you remember that electrician that had changing the ballast over here? He measured the voltage phase to phase and phase to ground, and he determined that it was de-energized. This eliminates or makes redundant the measuring of the voltage. Because according to Z462 and NFPA 70E, what someone has to do to properly ensure that the system is de-energized is measure phase to phase, phase to ground, and then take that meter and check it to a known source. Right? This does everything all by itself. So when you have a ground fault, it also determines if you have a ground fault. You have a flashing red light that tells you that you have a fault on a particular phase. When the disconnect is open, if you notice, I have three red lights indicating that the line side is on and three load side lights are on. So I measure L to ground, L2 to ground, L3 to ground. If the disconnect is open, those three lights go off. Can we say the system is de-energized? Just because the voltage is on. Just the indication is off, right? Can we say that? I'm going to jump up and say no, we cannot. Because these lights are off. Does that mean my switch is off? Or I have a burnt up bulb? Or in this case, no bulb at all. All we can say is the lights are not on. So we test the push button. There's a push button, test button right here. And we test the button, it says I'm thinking. It's going to go out there and it's going to measure phase to phase, phase to ground. If it comes back for less than 3 volts, you get 3 green lights, meaning it is truly de-energized. So it has performed the test similar to the way Z462 says you have to perform the test. Now you can safely enter. Would I say that you don't have to check it again? You're going to check it again. You can hit the button again, or you can check with your meter again. But it gives you a level of degree of confidence that that energy is de-energized. So we have issues sometimes with variable frequency drives. I'm going to try to do this quickly too because... So here's one manufacturer who says that there's 2 jumpers that have to be made. You have to alter these 2 jumpers in order to make the drive compatible with a resistance grounded system. Okay? You have to disconnect it here and disconnect it here for basically these types of systems, non-solidly grounded systems. And it says here, a non-solidly grounded system is an AC fed ungrounded system, so an ungrounded system. An impedance grounded system, so an impedance grounded system. B-phase grounded system, right? And a DC fed from an active inverter. So you have to remove 2 jumpers. And the benefits of that is it helps avoid severe equipment damage when a ground fault occurs. Not only that, but the B-phase grounded system, it's permanently ground faulted, right? So, and it helps prevent, that's not true because what you're looking at here is you have to disconnect the MOVs, and we saw what happens with MOVs if you have elevated potentials on 2 phases. And unfortunately with the B-phase grounded system, you're going to have 2 elevated voltages on A and C. So you're going to have 600 volts on A, 600 volts on C, 0 volts on B, and your MOVs will do what they're designed to do. The equipment doesn't fail. All it means is the equipment is going to do what it's designed to do. The only thing that's failed is the person who installed it, because they didn't put the right jumpers in. And the DC bus mode caps. Same manufacturer, 3 jumpers this time. MOV, always have to disconnect the MOV because the MOV is not compatible with a B-phase grounded system or when 2 of the phases are elevated in potential. And that's what happens when you have an ungrounded system or a resistance grounded system. 2 of the phases are going to be elevated. Not always A and C. Sometimes it could be A and B. Sometimes B and C. And they even show you where the jumpers are. Connected, disconnected. Connected, disconnected. Connected, disconnected. Another manufacturer. Anybody do work in Europe? They have a system over there called an IT system, which is different from a TN system. A TN system is a solidly grounded system. IT system is an ungrounded system, because you're looking at potential. Different manufacturer. What they have here is, I love this one, okay? A ground capacitor switch. What does that mean? It means you have to do more reading, that's what it means. Right? So we did more reading. A grounding capacitor switch allows the user to quickly change the value of leakage reduction capacitance of a 3-phase input circuit. See figures 4, 5, 6, 7, 8, 9 on page 19. It's all clear now, right? So we look at the figures. That's the switch there. What we did is we moved the capacitance. Because variable frequency drive manufacturers think that, well, and UPS manufacturers think that ground is this infinite, miraculous place where all unwanted frequencies can go. Right? When you have a variable frequency drive, you have pulse width modulation, you need to filter out that stuff someplace, send it to ground. So what happens when you have a capacitor on the front end of this thing and you have all this high frequency switching? What does the impedance of a capacitor look like when you have high frequency switching? Short circuit. All the frequency's gone. Variable frequency drives. Many people seem to think that variable frequency drives are separately derived sources, much like UPSs. A UPS is not a separately derived source. The only time you're going to have a separately derived source is if you go through a transformer. A variable frequency drive is not a separately derived source. I'll go through this quickly. This is a schematic of a variable frequency drive, right? Very simple. When you have, all right, here, diode 1 and diode 6 are forward biased. So you're conducting A and B phase. So you're energizing the DC bus with A and B phase. Now you're looking at 1 and 6 and 1. 1 and 2. 1 and 2 still. 2, 3. 2, 3. We're always forward biasing those diodes in such a manner that the DC bus, 1/3 of the time is energized by A phase, 1/3 of the time it's energized by B phase, and 1/3 of the time it's energized by C phase. And that's one cycle from here to here. These are degrees. So it's not really a separately derived source. What we're doing is time sharing the DC bus, although they're not paying the same rates you would pay in Miami. So when it's filtered, it looks like this. So when you have a fault on the DC bus, where does the current go when you have a ground fault? We discussed this earlier. Back to the source. How does it go back to the source? You have a source that goes right back here. So what are we doing? We're impressing DC voltage across that resistor. But all 3 phases see that fault. We had an old DSP system on a hospital near here, Brampton Hospital, brand new hospital, they put in an old DSP system. They had a fault on the output of a variable frequency drive. And what we noticed was that all three lights are on. The DSP system is such a device that it tells you what phase the fault is on when you have a fault. But all three of them were on. Well, you can't have a fault on all three phases. But they were time sharing the fault. So the fault was on the output of a variable frequency drive. Sorry?
Before the drive, actually. Not before the drive, before the...
No, if it was before the drive, it would only be on one phase. After the drive. Because remember, on the DC bus, all three phases contribute voltage to that DC bus. And on the output of here is dependent on this voltage here. Well, all three voltages here drive that voltage, and this comes from this.
You usually have on DC bus have some protection to protect that.
On the DC bus, yeah. Okay, let's look at it practically. If you had a variable frequency drive, how big is a DC bus?
It's
Half an inch? A quarter inch? A terminal? How big is it? It's not very big. It's more practical that you're going to have a fault on the output of a variable frequency drive because that's where the motor is. Correct? So let's see what happens if you have a fault on the output at the motor on a variable frequency drive. What do you think is going to happen? Let's take a guess. What does this side of the room think? I'm going to tell you. You don't have to guess anymore. This is normal. A, B, C, and that green line is neutral. This is the DC bus. So you have a fault on the output. Let's see, for example, when you have a fault on the output, let's assume your voltage and frequency is 50%. You want the motor to run at 50%. So now it's 160 hertz, you're running at, 60 hertz, you're running at 30 hertz. But you have to maintain the volts per hertz on the output of a variable frequency drive. So you're going to get half the voltage and half the frequency. If you have a ground fault on A phase at the motor, the current has to go back to the source, right? The current is going to go back to the transformer and it's going to complete the circuit. But when it goes back to the motor, when it goes back to the transformer, it has to go through the resistor. But it's operating at 50 hertz and you have half the voltage. So you could have 100% fault and you're getting half the current. And the current going through the resistor is at 30 hertz. Our DSP relay can detect that because we measure all three phases and we measure the current.
But DC bus is not insulated from the ground?
It is insulated from the ground. What?
But when fault happen on the DC bus,
Yeah.
how can I coming back to the source?
How does it come back to the source? If you have a ground fault on the DC bus, that means your connection here, you have this point here, the positive bus is connected to ground. That's what a ground fault would be on a DC bus, right? So now you complete your circuit. It goes this way, and it goes either here, here, or here, back to the DC bus. And you complete the circuit.
You're making ground fault to each phase equally.
Yeah. On the DC bus,
Yeah.
1/3 equally. On the output, it's different, a little bit different, because if you have a ground fault on the output of a variable frequency drive, it depends on the speed that you're operating that motor. You could be running at, let's say, if I got a 50 hertz fault here. Here. There's the input, there's the output. And the output doesn't really look like this. The output is actually pulse width modulation, and the inductance of the motor makes it look like a nice sine wave. So you can see that when you have a fault on A phase, 2/3 of each phase is time shared with that fault. So, when it comes to testing, we've had a lot of issues with testing high resistance grounding systems with applications. There's so many times that people get things wrong. And I'm here to tell you the right way of doing it. You can put a fault on the system. And what we do when we test and commission a high resistance ground in the system is to ensure that when we put a fault on the system, not only do we detect that the fault is there, but we detect that this phase and this phase elevate the full phase-to-phase potential, and we ensure that the connected load is compatible with the resistance ground in the system. Right? So we try to connect as much of the load as possible, put a fault on the system. Now, not many electricians like to connect a wire to C phase, the other end to ground, and turn on a switch. In fact, they sort of look at you like you got 4 eyes when you ask them to do this. And you can see why, right? So we can put a fuse, a 10 amp fuse in there. If we put a 10 amp fuse in there, it should be okay. If there's a problem, the 10 amp fuse will blow. Right? If that happens, we put a resistor in there as well. Now what happens? If we have a fault here, and we have 74 ohms in the path, we're going to get just under 5 volts, 5 amps. If we get under 5 amps, we're good. That means the load is compatible with the resistance ground in the system, and it's truly a resistance ground in the system. If we get 70 amps, and we blow the fuse, what happens? That means we have a solidly grounded system. Where are you allowed to ground your electrical system? You can ground it at the transformer, because all transformer manufacturers like to have this 1/4 by 2 inch copper link between the neutral bus and ground, the XO and ground. And nobody ever removes it. You're also allowed to ground it at the first switch. And electricians don't always remove that ground. So when you have an electrical system and it's resistance grounded, you have to ensure that the system is made to look that way as well. We had one facility here where they had just that. Resistance ground in the system, transformer, resistor, and we put a ground fault on it. The 2 phases did not elevate, which means it was solidly grounded. We're getting 70 amps of current. And nobody commissions this kind of stuff before. We have another system where they had a generator and a transformer, and when they were commissioning it, they were blowing the fuses. They couldn't understand why they were blowing fuses all the time. Now this transformer, there was no distributed neutral. This transformer went directly to the resistor and tied to ground. They measured the ohmic value, 69 ohms. They had a ground fault and destroyed all the cables that are going in here. So you knew something was wrong. I went there to commission this, and what happened was, they found that they had a 480 volt elevator, old elevator. So they used an auto transformer for the old elevator. And see that green wire there? That's the XO-HO bushing. That was tying the entire system to ground. So even though we had a resistor up here, that wire made it solidly grounded. And I had 3 of these things. So that prevented the neutral from shifting because we were tying it to ground. Incidentally, when you use a system like this, a transformer and a generator feeding one bus, most data centers are like this. We can have one of our DSP systems on here and control both of the resistors. So one high resistance grounded system will monitor the entire section. Even though we have 2, they're never on at the same time. Circuit breaker 1 and circuit breaker 2 are never tied together. They're never closed at the same time. One is always a backup of the other. So when you have a ground fault here, that current goes back here, that current goes back here, but we're detecting it the same way. So rather than have 2 high resistance grounded systems, one here and one here, we have one high resistance ground in the system, and we can monitor where the current is going. This is the first instance I told you about, what they had the surge protective devices. Only I showed one, they had 100 of them. Any questions? That was great, right on time. Unfortunately, I went through that very quickly, but. Any questions?
So everything was clear, I guess. Okay, we're gonna split the room in two groups. We're gonna start a plant tour and some demos, and then we will come back to this room for lunch. So we have to go one group first and the other.
Where's my work?
This group first.